Okay, I'll try.
All right, I'll go ahead and share screen. Can everyone see these slides okay?
I can take care of the chat, by the way. Yes, people can see this.
Fantastic. All right. So if I can get this in place, we'll get started. Fantastic. So this hour-and-a-half review session is going to be on tree recursion. So this is kind of an intro, basic look at tree recursion on this slide. The purpose of tree recursion is to think about how we can break down our problem into multiple different subproblems. The way we do this is by making multiple recursive calls. So each one of these recursive calls is going to represent a choice that we make. So for example, in the count stairs problem, we had one recursive call for the choice of taking one step and one recursive call for the choice of taking 2 steps. Whereas if we're working with lists, often a common choice that we make is whether we want to use a current element or not use a current element. Either way, the recursive leap of faith from our regular recursion problems still applies. So we still have to make sure that we abstract away all of the details of moving through each one of our function calls and just think about how do we get from where we are now to where we want to be in the next step. So just one level down in our recursive tree. When you're working on problems, the best thing to do is look at a doc test for tree recursion. You can write out what each one of these subproblems is going to reduce into. So for example, if you have a number, think about what are the different ways that we can reduce that number down and what are the choices that we are making that correspond to those. For each of those subproblems, go ahead and write out the corresponding recursive call and what you expect that return value to be. So going back to that leap of faith, make sure not to go further down into the stack of recursive calls. You want to start up here at the top, go one level down, and then not worry about the rest. So you're going to assume your function is going to correctly give you the right output at the subproblem. So for example, if you're trying to process a larger list, you want to assume that your function is going to give you the correct output if you call it on a smaller list. And then at the end of the day, we want to figure out how to combine the results of these subproblems together. Any questions so far? That was a lot. And if you have any questions, go ahead and unmute or ask in the chat. Oh, looks like I'm seeing something in the chat.
I can take care of the chat. I can.
Okay, fantastic. All right, so if there's no questions, I'm going to go ahead and move to the next slide. And again, feel free to stop me whenever you need to. Okay. So tree recursion, like we were talking about before, is going to involve multiple subproblems. So if we look at the Fibonacci tree on the right side, note that we're making a choice between 2 subproblems at every layer of this tree. So if we start at Fib 4, we're thinking about, okay, I can either reduce this number by 1 or I can reduce this number by 2. So this is a choice that we're making. And because of these choices, we get a branching factor that causes a tree-like structure in our function calls. Right? So this is just a visualization of what's going on over here. So if you can take a look at the left box that says common structures for tree recursion problems, this is a very bare bones look at one possible structure of any tree recursion question. So if we have a function that takes in some parameters and is tree recursive, we could think about this as having some base cases. So these base cases represent our simplest possible inputs, and here they're represented by this if case. So note that this isn't always the structure of a tree recursive question, but it's useful to think about how can I break this down into base cases and recursive cases. In our else case, take a look at these 2 function calls that we have here. We have a one call to tree recurse func on like a first input, a smaller subproblem that we choose, and a second call on a different smaller subproblem. And what we want to do is we want to combine these with some kind of operator. So this can be a function call or any sort of combination that we want to put these two together into a meaningful result. I want to emphasize that you can often have multiple function calls that you're going to be combining in multiple recursive cases that we're working with, but it's useful to come back to the structure to think about, okay, what is kind of the bare bones approach to these questions? All right, Sean, do you want to talk about the chips for tree recursion?
Sure. So if you want to click ahead a little bit, my formatting might have been really screwed up by PowerPoint, so I apologize if it looks really ugly. But yes, so as was mentioned before, you want to know your base case and your recursive case, but I think for true recursive problems, it's more important than ever. As Amrita mentioned, you're really just your brain is going to explode if you try to go all the way down a true recursive problem. Unlike a normal recursive problem where you can kind of track it to the end, it gets exponentially crazy. So you really, really, really have to take the recursive leap of faith. So apologies for the wall of text, but these slides are for your reference if you want to read them later. And yeah, so I think whenever you're doing true recursion, any type of recursion, but especially true recursion, the domain, range, and intended behavior of your function are the three most important things. So you can think of it kind of like a mathematical function. There's certain types of values which your function can take in. So for example, with our tree recursive Fibonacci function, it can take in positive integers, right? That gives you a natural idea for a base case, which is what happens if we reach the edge of our domain, right? What happens if we give our fib function 0 or 1? Because that's the boundary of our domain, it's a good choice for a base case so that we don't actually step outside of our domain. The second thing to consider is the range, which is very similar to the intended behavior, but I think it's really important to remember what type of thing your function is supposed to return. So a common problem with true recursive code writing is that say you have a function that's supposed to return a linked list, right? Once you reach your base case, you shouldn't return just a number instead, or like a Python list instead. You should return a linked list. So the idea is, in your base cases and in your recursive case, always return the same type of object for the most part. And you can use the recursive leap of faith to trust that your recursive call returns the same type of object every time. That is totally a mouthful. I know it's very confusing and abstract. We're going to make it more concrete as we go through some questions. But if you have questions in the meantime, feel free to put them in the chat or let me know, and I can clarify as best as I can. And Amrita is watching the chat. So with that out of the way, intended behavior, and that just means the recursive leap of faith. Trust that your function does what you want it to do. Now, why we use tree recursion as opposed to regular recursion is because you can encode decision-making into two recursive calls that follow different paths. So in general, if you have some problem that has a bunch of different types of options, for example, count partitions, there's like a ton of different types of partitions. The key is to break it down into one simple decision at the beginning, followed by multiple recursive calls. So you want to consider all of the possible options that you can explore and cut them up into disjoint sets. So for example, with count partitions, we can take all the partitions and say, let's split them in two. For some of them, we use the largest value, and for some of them, we don't use the largest value. We can use a recursive call to count up the number of partitions in each of those sets, and then we add them together and we're done. But again, the key is think about all the possibilities, divide them up into a simple decision, and recurse on each of those possible decisions. All this is super abstract, and it's here for you to read later, but it's just something to keep in mind when you're solving problems with tree recursion. And I think that's back to Amrita then.
Oh, Sean.
Yeah.
I think one thing that I have noticed personally, and it might apply for others, is that it's kind of easy to make your sets non-disjoint, and you need to make sure that the disjoint part is accounted for.
Yeah, so there is a danger. There is a danger whenever you're solving a tree recursive problem, as was brought up, that's a good point, that maybe those possibilities overlap. So when you're making that decision, make sure that none of the possibilities overlap with each other. There was another question, which was, what's the difference between addition and multiplication for tree recursive choices? That's an excellent question. And that really depends on the problem. So for count partitions, we add them together because we want to add together all the different partitions, all the different ways we can partition our number, right? Usually, sometimes you're going to see multiplication. I can't come up with an example off the top of my head. Amrita, do you have an example?
Yeah, I think multiplication might be useful, not multiplication between two recursive cases, but maybe if you're trying to build a number, you'd want to multiply to shift that part of the number over and then tack on a digit. Yeah, I can't think of any with multiplication between recursive calls.
Yeah, they probably exist. So if anyone has an idea, feel free to post it in the chat. And otherwise, I guess we'll puzzle on it and let you know later. Very good question. There's another question. Where can we find the code for count partitions? It's in the textbook. I think Amrita's going to explain the next part. I can pull up the page from the textbook and link it in the chat.
Fantastic.
Any other questions before we move on? Sister's jamming out. That's awesome. Okay.
Yeah. All right. So I think something that really helps with tree recursion, because it can be a pretty abstract concept at times, is to work through an example. So in this example, what we're trying to do is we're trying to sum the k largest digits of a number n. So we're given two non-negative integers n and k, and we want to return the sum of the k largest digits of n. So for example, let's take a look at this doc test here, which 2018 is equal to n, and 2 is equal to k. So what we're going to do is we're going to take 2 and 8, the two largest digits of 2018, and sum them together to get 10. And in 1, 2, 3, 4, 5, since we only have 5 digits, all of these digits are going to get included in the sum because k is greater than 5. All right. So with that in mind, we have some skeleton code over here. Note that this corresponds reasonably well to the skeleton code that we were looking at for our kind of simplistic example on a previous slide. Here we have an if statement where we're going to be returning 0. So here we want to think about what that simplest possible input is. Then we have two lines here where we're defining variables a and b. We want to return some function called on a and b. So why don't you take a few minutes, try to get started on this, and we'll talk about it together in a few minutes. So just as some things to keep in mind as you're getting started, like Sean was talking about on a previous slide, it's important to think about the domain and range for these kinds of questions. So here our domain is going to be two non-negative integers, n and k, and our range is also a non-negative integer. So we have to make sure that we're going to be returning an integer that is always non-negative or greater than or equal to 0. And just as some extra food for thought, think about for our base case, what's our simplest possible input, one where we give it to this function and then we're done. Then also, what are the different ways that we're making choices? We're breaking this problem down using n and k. Okay, we're going to move into breakout rooms. Before that, does anyone have any questions at all on the problem setup or the skeleton code that's been given? Okay, fantastic.
Are we going into breakout rooms or wait?
Yeah, I'm just going to go ahead and put you guys into breakout rooms. So everyone should have received an invitation as of now. Looks like there's still some people in the main room. Has anyone not been assigned to a breakout room? Looks like everyone's assigned on my end.
So we're thinking 10 minutes then?
Yeah, that sounds decent.
Okay. Yeah, and we can check in. I mean, I think you have the power to broadcast. So we can ask in like 5 or 6 minutes so we can say if people are done early, like, chat with each other. And then,
yeah, that sounds good.
Well.
I can go ahead and hop around from room to room after a couple of minutes.
That's a good call. Can you, am I co-host? I am co-host. So that means I guess I can too.
Okay, great.
Yeah, also I'm going to send, oh, sorry, what's up?
I hope the music isn't too distracting. I tried to find a quiet place in the house, but we'll see.
No, it's totally fine, especially right now. I mean, no one in there can even hear. I played piano for 10 years and bothered my family endlessly.
Oh, wow.
So I relate. So here is,
well, it looks like
you
there's
just make
something.
sure that link works. It's
Yeah,
just the two final problems. I realized that the quicksort problem from the slides wasn't really well defined. The problem was just like sort these numbers. And I was like, oh, I don't think that. I think I just gave a little more guidance.
Yeah, that's a good call. Yeah, I can see it.
Okay, awesome. Thank you.
Great.
What time did we put them into the rooms?
3:57.
3:57.
Yeah, we got some time.
That is true. It always feels like so long, like when people are working on problems. But then when I'm the one working on problems, it's never enough time. So.
Yeah, no, I get that. Especially on Zoom, it feels like I'm just staring at people for like a good 10 minutes.
Hello. Did you finish the problem? Oh, people are coming back.
Looks like people are coming back from their breakout rooms.
I'm gonna come up with some extra. I'm gonna go find some extra problems from like past tests.
Just in case we get done early. No,
yeah, or if people just want to like chew on some extra stuff after.
Hiya. Did y'all are y'all joining us right now, or are we coming back from a breakout room? Silence. Okay, cool. So we're working on this problem here, so feel free to discuss with one another. And then people are in breakout rooms and we'll come back in a few minutes. And Sean and I are also going to be hopping around between breakout rooms. Hi, how are we doing in this breakout room? Okay, so where are we right now, Brandon? What are we trying to work through? A and B. Okay. So are there any like specific questions or points of confusion that we have, or are we just kind of trying to talk through this? Okay, and anyone can feel free to unmute. Okay. How to break down the problem. All right. So let's think about that first doc test, right? We had 2018. We can think about just processing the last digit, right? And remember that in Python, in order to get that last digit, we can do n mod 10 in order to just grab that last digit for us. So there's two cases we can think about here. And this is a pretty common pattern in terms of tree recursion problems that revolve around numbers. And that is, are we going to be using that last digit, or are we not going to be using that last digit? So note that in the last line of the skeleton code, we have some function call on A and B, which means we're going to be returning some combination of A and B together. So what this means is that A and B have to be valid solutions to the problem, right? Or possible parts of valid solutions to the problem at least. So we can think about where we want to place these recursive calls and how many recursive calls there are just based on the structure of our skeleton code over there. Okay. Does that kind of help with breaking stuff down? Okay, fantastic. We'll give it a couple more minutes, and please, please, please talk to one another, either through the chat or verbally, and then we can hop back to the main room in a couple of minutes and go over it together. And are we all here from various breakout rooms?
Yeah, some people were coming back from those.
Okay, cool. I can go ahead and send out a broadcast then. Okay, looks like everyone should be back from the breakout rooms by now. I'm seeing some comments in the chat saying people were sitting in silence. That's a lot more awkward than talking about the problem. So to avoid awkwardness in the future, let's try and discuss with one another about what's going on. Okay, so let's get started. The first thing we want to think about is what our base case is going to be. What are the simplest possible inputs that we can have to our function, and what would happen if we passed in those inputs, right? So what we want to think about in this case is what is the simplest possible input for n, and what is the simplest possible input for k, and what happens in each case. So does anyone want to pitch in and think about, or say what they're thinking about in terms of what these base cases could be?
Okay, I would like to say that, well, the more apparent base case is when n is 0, because then you really have no digit, or you have just 0.
Mm-hmm.
And k would, and when, okay, so another base case is when k is 0, because then you can't tack on more digits.
Yep.
Some.
Fantastic, right? So if we look at the next slide, we can see that if n equals 0 or k equals 0, then we're just going to return 0. So fantastic, great. So the next thing we want to consider here is how can we break down this problem? So what we want to do is we want to think about what are the decisions we can make when we're trying to reduce this number into a smaller subproblem of itself. So let's say I have the number 2018. When we're working with numbers in Python, what we've gotten accustomed to doing is breaking this down using the last digit and the rest of the number. So let's try and continue that pattern. If we break this down into 201 and 8, now we have a decision to make. Is our last digit 8 part of our sum, or is it not part of our sum? And incidentally, we have two lines here that are going to be combined in some way in our return statement. So we know what we want to do is we want to take a combination of A and B. So A and B have to be potential solutions or parts of potential valid solutions for this question. So let's go ahead and assign A to be one of these choices, including or not including the digit, and B to be one of these choices, including or not including the digit. Let's say we do include this digit. Any ideas on what we should do to break down our recursive call? What should happen to n in this case? If we're going to be squishing down our number by one digit, what should happen to n? All right, so I'm seeing in the chat we have n mod 10. So n mod 10 is going to give us that last digit, and n florative 10 is going to give us the rest. So we want to use, though n mod 10 is going to be a part of the solution, we do want to use n florative 10 here. So that's how n is going to be broken down. If we're using our last digit as part of our sum, we've used up one of our k digits. So that means we're going to go ahead and turn k into k minus 1. And what do we do with that last digit? How do we incorporate it into our solution? Let's say I want 8 to be a part of the sum. What do I need to do? Do I need to multiply it with something? Do I need to add it to something? Yeah, add it back, exactly. So let me go ahead and switch slides. Well, first of all, we know these are going to be potential valid solutions, right? So this is what we're calling. And we've broken this down using n mod 10 and k minus 1. Fantastic. So now if we take a look at the next call, we're still breaking down n to be n mod 10, but now we're not using the last digit. So that means that we can keep this value k to be the same. We don't have to reduce it by 1. Any questions so far on how we're kind of breaking this down into two cases?
Can you go over why you don't reduce the k on like one of them?
Yeah, sure. So the reason that k isn't reduced on the second one in B is because we're not going to be using that last digit in our sum. So let's say I have 2018, right? If I didn't want to include the last digit, that means that I still have 2 digits remaining that can be part of my sum. But if I were to use 8, then I only have 1 digit remaining that can be part of my sum. So we've kind of effectively reduced the amount of digits we have left that we can add into our total. So if we don't use that last digit, we don't need to reduce that number of digits. Does that kind of help?
Yeah, thank you.
Okay, fantastic. Any other questions?
One more quick question.
Sure.
So when you were going throughout the process of doing what we did, what you said in the initial part of the slides, so you wrote out the sub-problems where you did 201 and 8, and then for those sub-problems, depending on which one we did, whether or not we're going to keep 8 or not keep 8, then that's when we wrote out the corresponding recursive call, correct?
Yeah.
And then how did you know that that was specifically the course? How did you know to delineate or deviate those two types of cases when we were going throughout the process?
Yeah, that's a really great question. For this particular problem, it's important to keep in mind what are the patterns of breaking things down that we've seen in previous recursive questions. So in previous recursive questions that involve numbers, usually we tend to break out that last digit and just move our way through until we reach the first digit. So that's one thing that we can use. Another thing we can do, and one that I really like to do, is to try and write out step by step how I as a human being would approach this problem, and then see if I can replicate that in code. So for example, if I take 2018, if I wanted to figure out what the largest digit was, I'd go ahead and grab 2 and then think about, okay, is 2 going to be part of this? Is 2 going to be one of the largest digits? I don't know yet because I haven't seen the rest of the number. And then look at 0. Okay, my largest sum so far that I've seen is like 2 plus 0, which is 2. And then if I look at 201, the largest sum I've seen so far is now 3, which is 2 plus 1. And then if I look at it 2018 as a whole, we've now incorporated 2 plus 8, which is 10. So we're kind of working our way, notice one digit at a time, and thinking about, does that largest sum change, or is it the same?
Okay,
in
cool.
Python, yeah, sure. In Python, it's a lot more difficult to move from left to right, so we can do the exact same process from right to left. Yeah, I hope that helps a little bit.
Yeah, thank you so much.
No problem. Okay, so yeah, go ahead, Sakshi.
Related to this specific problem, but in Python, supposing you just wanted to keep the first digit of n, and then call something recursively on the rest of it, like if that's what the problem specified, then how would you do that?
So grabbing the first digit of a number is a lot more difficult of a task, just because you don't know how many digits the number has. So off the top of my head, what I can think of is calling a for loop, writing a for loop that goes a certain number of times until you have a single digit number, and that's going to give you, or that just calls n florative 10 until you have a single digit number. That's probably going to be the easiest way to get the first digit. Unless, Sean, you want to pitch in any other way that you can think of that's a little bit less unwieldy?
Nope, I can't think of anything else off the top of my head. You could define a new number that, like an object that holds that as an attribute if you wanted to. But,
Ooh, data abstraction.
yeah, but with regular Python numbers, I can't think of an easy way. Maybe there is one though.
So that's kind of why we work from right to left instead of left to right.
Okay, thank you.
Yeah, no problem. Okay. So now we want to think about how do we combine these two possible solutions that we have. We know that we want the largest possible sum. So that means that we can take the max of each of these potential solutions. Note that that's what we were doing when I kind of walked through how I as a human would approach this. We were thinking about at each step, would 20 or 2 plus 0 be a better sum than 2 plus 1? So at every step of the way, we're kind of comparing. That's what's motivating this max here. Okay, any questions about how we're combining this? This is a really important step.
Sorry, go ahead.
You go.
Okay, so the max, is it like going through and like taking the max of A and B, and then somehow the recursion is looking at all the maxes and taking then the max of the maxes? It's just like, how is it keeping track of all of these different sums?
Yeah, that's a totally fair question. And this is where the recursive leap of faith comes in, right? So we don't want to think about taking the max of several other maxes. We just want to think about, okay, what is sum largest of n mod 10k minus 1 doing? It's saying, okay, what is the largest sum if I include the last digit? And what is the second B is, what is the largest sum if I don't include that last digit? So we want to say, okay, now we have these two possibilities. Let's say we look at 2018. we're thinking about here, A is the largest sum including 8, so that's going to be 10. And B is the largest sum that doesn't include 8, which is going to be 3. So now we want to compare between 3 and 8. Trust that the recursion can get those numbers 3 and 8 for us. Or sorry, 3 and 10. I can't add today, but 3 and 10, and then go ahead and see how do we get that maximum number. And Max is going to help us do that. So we're taking that recursive leap of faith and making sure that we don't try and work our way down these levels of recursion, because that's not going to give you a solution. It's just going to give you a bit of a headache. Does that help a bit?
Yeah, thank you.
Okay, fantastic. And Jethan, you had a question as well?
It was the exact same question that she asked.
Okay, fantastic. So now we want to think about, okay, what are we doing to modify each of these calls? So for this problem, if we take a look at what we were talking about before, we're just going to go ahead and add in that last digit. Okay, so that's fantastic. Now I have a question for everyone here. Our second line was sum largest of n florative 10 and k. Do we need to add anything onto here if we're not including the last digit? Anyone
We do
can go
not.
ahead.
You
Yeah,
don't
we
need to
don't.
include. You do not need to.
Yeah, we don't need to include it at all, right? Because we're not incorporating anything new with this step. So all we need to say is just sum largest of n florative 10 and k. So that's the entirety of this solution. Any questions about what's going on over here? Okay, fantastic. So in that case, I'll hand it over to Sean. You can.
Awesome. Okay, so what I'm going to do is I like to go through problems on Notability. So here is a link to a document that hopefully should give y'all a PDF that includes 2 other problems, and then there's a bunch of challenge problems, which are from exams at the end. I've included some notes about them. But just a heads up, I'm going to claim host and start sharing my screen. So if people can't see my screen in like a few seconds, let me know. Okay, hopefully people can see my screen now. So we're going to start with this collect candy function. And the idea is we're given a Python list of lists. And this is also described in the slides. So you can look there for a more precise description of what our lists look like. So for example, our first list would be 9, 7, 2, 5, 9. And then our second list would be 0, 7, and then ... And you can get the picture from that. So that is our grid. And we start out in some row number and some column number. And our goal is to proceed to the top left square and collect as much candy as possible, where the number on a square represents how much candy you collect from that square. We're constrained by the fact that we can only move upwards and to the left. Okay, so if you look at our skeleton code, I think we don't have a ton of time, but this problem I think is more straightforward than the last problem and the one before. So is this one a problem that could show up on the exam? Yeah, I mean, all this is certainly in scope. That's a good question. So, okay, so I added some notes here. I'd like everyone to think about some general strategies we could use here. So before we consider the base cases, let's say we have a complicated case, like we start over here on this green square, right? If we want to partition the set, so if we consider every single possibility that we have of moving to the top left, right? We can partition that set into 2 distinct subsets. So we have really 2 possibilities. And if someone who hasn't spoken yet would like to just let me know, what choice do I have here? Go up or go left. Great. So that's our choice. So our choice is go, oh, sorry. Choice is go up or go left. Okay. So if I go up first, then it's going to give me, by the recursive leap of faith, the maximum amount of candy that I can collect for a path that starts on that 4, on this one here. If I go left first, it's going to give me the maximum amount of candy starting from 2. Which one of these should I pick? What's our goal? We should pick, yeah, probably up, but like in a more abstract sense, if up gives me like 27 and left gives me like 16, which one should I pick?
Max.
I think this
Max,
is where
okay.
recursion comes in.
So this is where the recursion comes in. And then the idea is after we recurse, we need to somehow evaluate the results. Yeah, good, max of the 2. So to evaluate the results, in this case, we know we want to take the max, okay? So with these problems, I like the jigsaw puzzle approach, which is just sort of fill in what you know, even if you don't have the entire problem solved at first. And that sort of illuminates other parts of the problem. So now we have an idea of what A and B are. I'm going to sort of tag these. I think I'd highly recommend this. It's an online exam, but like I'd recommend making notes and drawing little tags like this. I'm going to say this is going up, and this is going left. Oh, that's not how you spell words. Oops. Okay. I'm going to need, one sec, guys. Let me turn on Do Not Disturb. Sorry. Okay. Apologies, we should be back online now. Let me know if you can't see my screen in a few seconds. Okay. So going up is just going to be a recursive call to collect candy, right? We know we have to recurse. Is the grid changing? Anyone want to tell me? No, the grid stays the same. Cool. So the grid's the same. Okay, if I'm going up, is my column changing? No, my column stays the same because I'm just going straight up. But my row changes. And something you should notice is that in a list like this, the top row is indexed at 0. The next one is indexed at 1. So if we go up, what should we do to the row number? Should we increase it or decrease it? Decrease. Awesome. Because we want to go up. Smaller numbers are closer to the top. So row plus 1. And I apologize to everyone for subjecting you to my handwriting. Now you experience the pain of my discussion section. So if we have, that's our call for going up. Let's just be lazy here and figure out, yeah.
Wait, when you go up, you're supposed to subtract.
Subtract 1. Yeah, it turns out a plus is not how to subtract things. Good catch. Thank you. I appreciate that. I will make mistakes, and let me know when I do. That's fantastic. Thank you, people. Okay, so when we move to the left, how do we change things? This is within this list, the leftmost is 0, and then 1, and then 2, and then 3. Yeah, same thing. We subtract 1, and this time I'll get it right. There we go. Okay. And the idea is if A has the amount of candy from going up and B has the amount of candy from going left, then we can just take the max of the 2. But there's one, there's 2 ways you could write this, but I'm going to write this on these 2 lines. There's one thing I haven't counted yet, right? Which square haven't I counted in these recursive calls?
The current square.
The current square, very good. So to index into the current square, we ask for the grid. And then if we want to get which list we're looking at, that's which row. And then we select the column number. And then that will give us this. And alternatively, you could have put this on the return line, but this is, yeah.
I'm not under, oh, okay. Sorry, just kidding. I was confused why that was put in front of the collect candy function, but.
Oh yeah, so it's the recursive call, which is how many can we collect after our first step, and then plus however many are on the square we're on right now. That's like the one square we can't avoid. That's a good question. Okay, so now we talk about our base case. When do we know we're done? When can we stop recursing?
Row and column are 0.
Awesome. If row equals 0, and well, actually, this this could be a little tricky because, yeah, okay. So if row equals 0, well, I think we might have, this
Wait.
might be a tricky problem because once we hit the top, we actually need several base cases. But let's do this for now. Yeah, what's up?
I think when I was doing this problem, I actually realized that you need to account for how do you make sure that you're not running off of the grid.
Yes. So that's the other thing. That's why I wish I had actually an extra case here. If row is 0, we want to return collect candy, and this is going to get really ugly, so I apologize. I'm going to draw an arrow. Collect candy of grid, and then, well, okay. There's two things we can do. If row equals 0 and column equals 0, then we can safely return just the final square. However, there are a couple extra base cases. So remember when I talked about domain, I said consider the possible values that each of your inputs can take. So row has to be a positive or non-negative number, and col also has to be a non-negative number. So what happens if we just race up to the top? What prevents us from jumping off the edge and getting to negative numbers there? And that's where I'm glad I didn't put you all into breakout rooms because we're missing a couple base cases. So if row equals 0 and the column is not 0, then we're going to have to recurse on what? Actually, oh no, there's one simple base case that can maybe solve all this. Yeah, there's one simple base case that solves all of this. Do people see it?
Oh, yes.
Yes.
That's if row is less than 0 or column is less than 0.
There you go. Good.
And that way you can just return 0 at the end.
Very good. Okay.
And why it
so
works is because, well, partly because you don't have negative candy.
That sort of is it. Yeah, you don't have negative candy, but more importantly, you don't have negative spaces on the board. Unfortunately, I'm not actually able to scroll right now because that ability is being annoying. There we go. But the idea is, once we get to the top here, there are two options. And the two options are, we can either move left or we can move up and just quit. But we can't move up and just quit. And it was mentioned there's no negative candy, which means that it's always strictly better to move left than it is to end the sequence here. That's like a very confusing explanation. But if people have questions about this, I would totally understand because this is kind of haphazard. I should have checked the slide answers before. Any other questions?
Question. So is there only one, is this the only base case there is?
Yeah, so in this case, if you frame it like this, you only need one base case.
Okay, so when you reach the top left corner, but then don't you still go left or up?
Yeah, so good question. Do you still go left or up after you reach the top corner? And the answer is yes. So we add in this 9 and we recursively go left and we recursively go up. But in both of these cases, we have a negative coordinate, which means we just return 0 and we stop recursing.
Oh, okay, got it. Thank you.
Yeah, no problem. Cool.
I have a question just on the goal of this problem. I was kind of confused on it. Or is our goal to find the path with the most candy from the given row column to the top left corner?
Yes, that is the goal.
Okay, thank you.
Yeah, sorry, I think that was more explicit on the slides, but I should have put that down here as well.
I have a question as well.
Yep, go for it.
So when you hit 5, you want to go left, but then wouldn't that be the base case already?
Which one? This one or this one?
Yeah, 5. Yeah, 5. The top one.
Oh, the top one. Yeah. So there's 2 recursive calls from 5, right? There's A, which goes upward. And when we go upward, you're right, you hit the base case, but we also go left. And in that case, we keep recursing.
Oh, gotcha. Thank you.
Yeah, no problem. Anything else? All right. Yeah, it's a good solution for negative candy, unless you have infinite negative candy, in which case the problem starts getting a little tricky. We're gonna move on. I think the next question is Amrita's.
Yep. Let's see if I can. Oh, looks like Sean.
Oh, I
I'm
still
not
host from you.
anymore.
I'm gonna
Yeah.
make you host. Sorry for the coup.
Yeah, no
Okay.
problem.
You're host now.
Okay, great. My power has been restored. Let me go ahead and share screen.
Sweet.
Oh, give me just a second. We're having some technical Google Slides difficulties, but we'll get there.
PowerPoint is better.
PowerPoint is better. Oh my goodness. Okay. Let's see. Okay, we're good to go. And yes, co-host is a good solution. So we'll go ahead and do that in a second. So the next problem, first of all, is this slide blocked out for anybody by faces or the chat or anything like that? Okay, I hope there's no, okay, no, fantastic, great. So our next question is going to be count sequence. So in this question, we're going to be given two lists, list and seek. So seek is contained within list if all of the elements of seek appear in list in order and not adjacent to one another. So what does this mean? This is kind of a strange phrasing, but let's go ahead and look at an example. Let's say list is 1, 2, 3, 4, 5, and seek is 2, 4. We want to figure out how many ways can we find 2, 4 in that order and not next to each other inside of list. So here we can see that 2 and 4 are highlighted in red, and there's only one way that we can find them. So I'm going to skip this, or actually this second case here is where 3 and 4 are adjacent, so they don't count. So note that here we have 0 ways that seek is contained within list because 3 and 4 are next to each other. For 1, 1, 5, this is where things get interesting because we have multiple ways that 1 and 5 are contained in here. We have this first one combined with the last 5, as well as a middle one combined with the last 5. So that results in a total of 2 non-adjacent ways. And for this last example, 4, 2 are not contained in order, so we have 0 ways. Any questions about problem setup? I know this can be a bit confusing.
Are we going into break room towards this?
No, I don't think so. Right? It seems like we're running a little bit low on time. Sean, what do you think?
I think it's okay if people work individually in the main room if people don't mind.
Yeah, that would be fantastic. And you feel free to like talk and discuss with one another in the main room as well. Okay, great. So fortunately for this question, we're given quite a considerable amount of skeleton code. So one of these doc tests is included up here. And let's think about domain and range. Does anyone want to tell me what the domain of this question is? What kind of values are we taking in?
The domain would be lists.
Exactly, right? And 2 lists. Fantastic. So what would the range be? What kind of values are we outputting? Let's see. Yeah, non-negative integer. Fantastic. Okay, great. So here we have a couple of different if and elif cases. So things to think about would be what are our simplest possible inputs? And then also for our recursive case or cases, how do we break this down? So why don't we take a few minutes and try and work on this individually and go ahead and collaborate with one another in the main room if you feel comfortable doing that. So over chat or on verbally. Any questions about the skeleton code and how it's set up? Okay, great. I'll disappear for a bit so y'all have room to talk to one another.
Hello? Hello, a question in the given example.
Mhm.
And it shows 1, 2, 1, 4, 5, and
Yep. So,
so,
we have, oh, go ahead.
so always count from left to right to see if the other list. I think I get it. Yeah, thank you.
Okay, yeah, no problem. But just to go over one more time, what we're doing here is we're trying to find this sequence 1, 5 inside of 1, 2, 1, 4, 5. So note that here there's two ways to do that, the 1 in the front and the 5 in the back, and also the 1 in this middle and the 5 in the back. So we can combine those to find 1, 5 and 1, 5. Good question. Okay, let's go ahead and start walking through this together. The first thing we want to think about is potential base cases for this problem. So for base cases, what I like to do is I like to think about, okay, what is the simplest possible input for each one of my variables? And that helps us put us on a path to thinking about what our base cases could be. So let's start off with seek. What is the simplest possible input of this subsequence that when we get it, we'd say, okay, we're done? Empty, right? Exactly. So if sequence is empty, we want to go ahead and return 1, because there's only one way to find an empty subsequence inside of a larger sequence. Okay? So now what we want to do is we want to think about what would be our simplest possible input for list. Also empty, exactly. So if list is empty, how many ways can we find seek inside of list? 0, exactly. So that's going to be our next base case. Okay. So we've kind of exhausted working our way through list and working our way through seek and thinking about what those base cases could be. So are there any other, oh, looks like we got a question. Why the first base case returns 1? Okay, yeah. So this is kind of a subtlety of lists where in this problem, we're thinking about an empty list as a sub list of a list with items in it. So for example, any list like 1, 2, 3 or like 2, 3, 4, that's always going to have an empty list as a sub list. Because if we pick out nothing from that list, that gives us an empty list back. So that's kind of a subtlety of this problem, where seek is returning 1, or this problem is returning 1 if seek is empty. So that's what's happening. So an empty sequence is always present inside of a larger sequence of numbers. Does that kind of help? Okay, great. So now what we want to think about is how can we break this problem down? How do we move through this list? So a hint for this problem that I think was given on a previous slide was to use slicing. What we want to do is we want to work through numbers we work through from right to left, remember. But lists, it's easier to work through them from left to right. So if we want to go ahead and work through this list from left to right, let's try and consider the first element of this list and think about how that would factor into our solution. So in this case, the first element of our list is 1. And the first element of sequence is 1. Fantastic. Now we know that we're at least on a path towards working toward finding this sequence inside of list. So what we can go ahead and do is think about, okay, if they're not equal, let's say this was like 7 or something, that means that we can really discount it as a potential part of our subsequences that we can find. So we can go ahead and kick that out and just think about this as 2, 1, 4, 5, and then finding 1, 5 inside of it. This is kind of encompassed by, So let's go ahead and block out that last line from our general vision. Should have edited this earlier. But if we think about where list of 0 is not equal to sequence of 0, then we're going to return count sequence of the rest of list and all of seek. So what we're doing is we're discounting that first element. Okay, any questions about that recursive case over there? This first one, ignore with first.
As a quick question, when you were going through, how did you come to that as your if case when you were looking at it for the recursive call? Because how did you break that down from the sub problem to get to that recursive call?
Sure, right? So one way we can go about doing this is thinking about what our doc tests are. So if we look at some previous doc tests, there's one where the first element is not equal to the first element of our sequence. So in that case, we can just go ahead and discount it. So when we discount it, what are we doing? We're making our list smaller. We're trying to break down this problem. And the way we can make this list smaller is just by removing that first element and getting a slice of the rest of the list. So that's essentially what's motivating this case over here. Just working through these different doc tests. Yeah, I know it can be a bit challenging to see at first.
Okay, cool. Thank you.
Yeah, no problem. Okay, now let's go over to this revealed mystery over in the else case. What we want to do is we want to think about what are the choices we can make if the first element of our list is equal to the first element of our sequence. So either, much like our previous problem, we can either include it or not include it. If we include it, that's going to be one recursive case, and if we don't include it, that's going to be another. So if we were to include this, we know that the next element cannot be a part of our subsequence because the sequences cannot be adjacent to one another. That was specified in the problem spec. So we can go ahead and squish this list down by 2 because we know we can ignore that element next to 1. So in this case, we're getting rid of both 1 and 2 and just considering if 5 is in the rest of that list. And since we used up this 1 in our sequence, we're breaking down sequence using slicing as well. Okay, so in the other case where we don't use with first, we use without first. So if we don't use that 1, that means that the sequence 1, 5 is going to be present somewhere else in the rest of our list. So in this case, we'd call count sequence of the rest of the list, which is list of 1 colon, and the entirety of sequence because we're not using that first digit. So these are our 2 cases. Any questions about how I'm breaking this down? I know that was a bit fast.
Can you go over the second case with the without first again, please?
Sure, absolutely. So in this example, let's say I don't want this 1 to be a part of my subsequence that I'm finding, this first red one here. Well, they're both red, but the first one. So I can go ahead and get rid of that 1 and just think about, okay, is the sequence 1, 5 present in the rest of my list? And how many times is it present if it is? So let's say we get rid of that first 1. How many times is the sequence 1, 5 present in the rest of the list?
We get rid of the first one, it's present one more time.
Yeah, exactly, right? It's just present once. And if we keep that first 1, then we know that 5 is present in the rest of the list 1 time. So we can find 1 sequence that way. So
Okay,
that's
cool.
how we know we're breaking this up.
Okay, cool, thank you.
No problem. Okay, any ideas on how to combine these 2 together, with first and without first? What do we want to do?
We add, correct?
Exactly. We want to go ahead and get the total number of ways that we can find this sequence. So we're going to add with first plus without first. Okay, that was a lot. Any questions about this? Oh, looks like we got one in the chat. Oh, Sean, you got that one? Or do you want me to? I can talk about it as well.
Might be faster if you talk about it.
Okay, great. So where are we checking to see if the number next to 1 isn't the next number in sequence? Oh, that's fantastic. Okay, so the way we're doing that is in our with first case. Notice that we're slicing list of 2 colon instead of list of 1 colon. What this does is it go ahead and discounts the first 2 values in our list and just looks at the rest of it. So when we've used this 1, we're just considering 1, 4, and 5. We're not even thinking about 2 as the potential completion of this sequence. I hope that helps. Okay, we have another question here. How will the second case act differently from the without first case? That's a good question. It doesn't. It's just useful for us to think about, okay, we want to specify that in this condition, we want to do the same recursive call as in the without first case. So just syntactically for us, it's easier to see. And also, we have to specify that in this case, we want to make that recursive call. So great.
Oh, question is, well, this is probably for general. How do you avoid double counting in these sorts of problems?
So generally to avoid double counting, I think it's one way to do that is to, yeah, you're right, it's tricky. But one way to do that is to draw out a little diagram. So if you draw out a tree diagram of what calls you're making, like we did for Fibonacci, that's going to make it pretty difficult for you to recount stuff that you've already counted because you'll visually see it there.
Yes.
Make sure to do this for a small input, but yeah, that'll help. Okay, great. So with that in mind, let's go ahead and move on to the next question. Sean, do you want to take over?
Yeah, sounds good. And I wanted to address one question in the chat in a faster way than typing to it. I was asked if the only time when we increment the count is when the sequence is empty, how do we end up getting the right count? Which I think is an excellent question. And the main reason for that is if we were, I can show you visually in a second, but yes, you're right. The only time we actually add a number is once we reach the base case. So the question is, how many times do we reach that base case? And we only reach that base case once we've constructed that full sequence, right? So we count up the number of times we reach the first base case by adding together all these recursive calls. And that's equal to the number of times that we've constructed a valid sequence. And I can draw it out as a tree in a second. Am I co-host? Oh, I am. Thanks.
Yeah.
Okay. We don't have a ton of time left, so we're going to just jump into one question real quick, and I'm going to draw out what I was talking about earlier. So in general, when you have a true recursive thing, it looks something like this, right? Maybe there's 3 calls, maybe there's 2. In our problem, it looks like mostly there's 2 calls, and then eventually things hit a base case. So let's say we mark this one as 0, this one as 0, and these ones as 1s. So the only time we're actually adding a value is when we reach the base case. But at the very top, as we add them up, we count the number of successful times, the number of times we successfully reach the base case. And we only reach that if we construct a valid sequence. So I don't know if that helps or not, but hopefully that helps.
Yeah.
So,
And oh, sorry.
Yeah,
just to add on to that real quick. Whenever we delete an element from sequence, that means that we've found that element in list. So if we've reached an empty list for seek, that means that we've found all of the elements in sequence. Just logistically, that's what that means.
Awesome.
Yeah. Take it away.
Yeah, so again, I think in the interest of time, we're just going to go through this one. And then that will leave maybe, hopefully, a tiny bit of time for people to just ask questions in general about true recursion. But the challenge right now is sorting values. We can think of them as numbers, but this is a really central question to all of computer science. So it's a cool thing to think about how we can do this tree recursively. So first strategy we're going to talk about is merge sort. And the idea is we take a list of numbers and we cut it in half and we sort both sides, and then we merge them together to get a final list of sorted numbers. So the reason I'm explaining this algorithm instead of letting y'all derive it is because I don't think it's immediately obvious. I just think merge sort is a good thing for everyone to see if you're learning tree recursion. This is the algorithmically fastest, and this is out of scope for the course, but this is the fastest way to sort numbers in a comparison-based way. So just like a really simple tree recursive function is super, super fast. So if we're sorting a list of numbers, what do you think our base case is?
Well, that's when you have a list of lengths 1 or 0.
Yep, so we're going to simplify that and just say, let's take a list. If our list is empty, then it's already sorted for us. So that's kind of nice. So if we have an empty list, we don't really need to do any work. I think base cases can get kind of confusing when you get into these weird sort of pedantic cases, but that's how we're going to start. Otherwise, we're going to divide the list in half. Does someone who hasn't spoken yet want to say a way that we can divide the list in half? I can't read the chat right now, so if you type it in the chat, I would appreciate if Amrita could tell me.
Yeah, absolutely.
Thank you. Any ideas? How are we going to cut this list in half?
I believe we can cut the list in half by.
Sorry, just for participation. Yeah, it's okay.
Not seeing anything in the chat.
No responses. All right, go for it. Sorry for cutting you off. Just wanted to try to foster some participation.
Oh, I think we can cut these. I might be wrong, but we might be cutting these to halves by the order. Well, we're going to cut them off by the order of the. Well, which the head of the first list is going to be smaller than that of the second, or could that be?
So, yeah, so there might be some differences in the sizes of the lists, but that's actually okay. It's okay if they're not divided perfectly in half.
And I'm
So
seeing
what we
len
can-
function in the chat.
Awesome, awesome. Yes, len function is going to be our friend here. So we're going to use some list slicing. And the first thing we're going to do is we're going to call len on list to get the number of items. And we're going to floor div it by 2 to get an integer, which we can use as an index. And we're going to take all the numbers up until that middle index, and then all the numbers after that middle index. And these are our two half lists. So what do you think we're going to do with those?
Are we gonna add up the merged versions of each? So we're gonna do like merge of A and merge of B, and then we're essentially just gonna add those two pieces up.
Good. So we can add them up, but the thing is, once we sort them, let's say we have like 1, 2, 5, 6, 7, and then we have like 3, 5, 7, 9, 12. If we just put them right next to each other, we don't know, like we have to sort of interleave them together, right? And this is where there's a little bit of an abstraction. And I put here, assume that you have access to a merge function. I think y'all wrote one of those you are writing one in your Scheme project. And I think there's also a discussion question about how to do this with iterators. But after you write that, it's like a more of a straightforward function than this one. You can call merge on A and B, and that will put these two sorted lists together into one larger sorted list, and you're done. Now, there's one other way we can do it, which is called quicksort. Quicksort is actually a lot of times faster than merge sort, which is kind of nice. And it uses a little bit of a different strategy to divide up the list. So instead of dividing it up into two lists arbitrarily and then merging the results, the idea is we pick a pivot. So I'm going to fill you in on the base case just in the interest of time. The idea is if we have an empty list, again, our list is already sorted, which is kind of nice. But here's the thing. So we pick a pivot, and we put the pivot in the middle of our final list. So what should go to the left of the pivot in our final list? Like, what is A?
Oh, well, you get a quick sorted version of the list of elements that are less than the pivot.
Good. So the idea is everything to the left of the pivot has to be smaller than pivot, right? So for that reason, we're going to filter out, we're going to use a list comprehension, right? This is why I wrote these lines like crazy long out of preparation. And we're going to use that list comprehension to only select items which are smaller than pivot. Okay.
You might want to include less than or equal to, or wait.
So there's two ways you can do
wait.
this. You can include less than or equal to in one of the sides. Alternatively, you can write a version of this that has 3 sorts. But if you note, we assume that there are unique values here, so that's okay. And then B, every item has to be larger. So you recursively sort A, you recursively sort B, and you stick them all together in a list, and the whole thing is sorted. And if you call, there's a built-in function called sort in Python. Most of the time, it uses merge sort for larger lists and then switches down to quick sort when you get to smaller lists. So this is actually how Python sorts things, which I think is kind of cool. Any questions on sorting using tree recursion? I think yeah, go for it.
Sorry, you just said something about something being out of scope. Like what exactly from what you just showed is out of scope?
Oh, yeah, good question. So I said, I was talking about how fast merge sort runs, and I said it was really fast. And that is out of scope. You don't need to worry about how fast it runs. Runtimes, like principled analysis of runtimes is not in scope for 621A.
Okay, thank you.
Yeah, all good. Any other questions? It's a good question. I think it's already 5:01. I'm going to stick around for a bit. Also, that document is available online. I think we'll post it on Piazza. I put it in the chat too. How do you do if there's a duplicate? So two ways. You can either set one of the sides to be less than or equal to, and then say strictly greater than. The only thing you have to be scared of is putting the same, like duplicating an item, like putting one on the left-hand side and the right-hand side. So as long as you make sure it's only on one side, that's fine. There's also a version of Quicksort that's faster, where you create three lists. You create a list of items that are smaller than the pivot, a list that's greater than the pivot, and a list that's equal to the pivot. And then you don't have to sort the list that's equal to the pivot, and you just put all of those items in the middle. That makes sense? I can explain further. I'm gonna check in on that. Oh, sorry, is there another question?
I have one quick question.
Mm-hmm.
So when we're going through our lists and we're going through our tree recursion process, how do we make sure that we're able to go in our process? How are we able to make sure that we're able to go from those subproblems to that recursive call? I'm still a little confused on that.
So the subproblems to the recursive call, like after you identify the decision you have to make, or before?
Before, I think, yeah.
Before. So step one is figure out what the subproblems are, right? So in the case, if we look at like our count candy example, thanks for coming. Our count candy example, we first identify that decision, right? Which is either to move up or to the left. If you look at the count sequences example, we also identify the decision, which is, do we count this as the first item of our sequence, or do we not count it as the first item of our sequence? So find some decision to extract first, right? Does that make sense?
Yeah, and then how we get those subproblems is off of that decision. So essentially we decide what to include, and from there we're able to draw what we need, and then we're able to build everything off of that by building on those recursive calls.
Exactly, and you can reverse engineer some of it. You can say, okay, I know what my base case is. I have to count down to that base case somehow, right? And for that reason, like for example, if my base case is an empty list, I should be doing something in the recursive calls to make the list smaller, right?
Okay.
So that can give you a hint as to what your subproblems might look like. Amrita, do you want to add anything?
Yeah, no, that's pretty comprehensive. And also, if you're feeling a little stuck about thinking what those choices are going to be, one trick that you can use is to think about what would be ways that we can break down each one of our inputs. So look at each of the inputs separately. If you've got a list, there's a couple of ways that we can break that down. If you've got a number, there's ways that we can break that down too. So that might help you get unstuck.
Okay. So break down each of our inputs, and what else?
Yeah, and then what Sean was saying about identifying those decisions and making sure that you can take those choices accordingly.
All right, awesome. Thank you guys so much.
All good, thanks for coming.
Yep.
Thank you.
For the pivot, why do we choose pivot's gonna be the first item of the list? Could be anything?
It's a really good question, and it could be anything. It's totally arbitrary.
Okay, perfect. Thank you.
Yeah, okay.
Is the PDF with the markups going to be posted anywhere?
Yeah, so I'm going to post it on Piazza with the resources. I think there's a Piazza thing about these topic review sessions. So with the recording will be a PDF with a markup.
Cool. Okay. Thank you guys so much.
Yeah. Thanks.
And it looks like there's a question about whether the PDF with your answers is going to be posted somewhere.
It will, probably with neater handwriting. So it will be posted with the recording of the session.
And the answers are all on the slides, except for merge sort, I think. So
I also added some challenge problems, so if you're feeling like a challenge, that's also going to be there for you.
yeah.
Excuse me. I had just a general question about like the demo exam that's posted on the website. There's like 3 different options for it when we click on the link. Like, is there one of them we just take like on our own, just like for practice, and which one do we actually choose once it comes time to take the demo exam?
I think, let me check for you actually.
Yeah, it might correspond to the 3 sections. I'm not quite sure. Let's see.
It's like midterm, demo, midterm, if I recall correctly. Let's see.
Yeah, one of them says like demo, one says test final, then one says practice final. Like
that's very ambiguous.
Huh.
If it's not on a Piazza post right now, then you don't need to know it. Although I will ping the teaching people who are in charge of like building that and ask them what's going on.
I just
That's an excellent question. Yeah.
We'll get back to you on that.
see what the exam looks like, you know, like
to see what it looks like. Try each of them. The password try the password on each of them. At least one of them should be available to you now.
Okay, I don't have to worry about like, not being able to take it again once it comes time to take it on the 24th, right?
No, no, no.
Okay, cool. Thanks.
Mhm.
Yeah, any other questions that people have just regarding tree recursion, 61A, life, anything you want to answer?
I'm just wondering, what are your predictions on the exam for given this weird format and the
So what do you mean by predictions? Like the type of problems you're going to see?
yes, the level of difficulty of problems firstly, that's because I know that the class had a bit of a hard time with midterm 1 and midterm 2, so given the statistics.
Yeah, I
Yes,
mean the
so,
class. Oh, go for it. You go first. Yeah.
Okay, so I think past exams, like things from previous semesters, are going to be your best bet in terms of determining the difficulty of the upcoming final. So if you can do those, you're in great shape for the final exam. So that's kind of where the difficulty is going to be, just pretty in line with previous semesters.
Yes. So one thing that I'm doing is actually going through some of the problems that I've done before, but I thought were hard, and going back again. Do you think that's still a good strategy, even though I've already learned
Yeah,
that?
I think, yeah, if you've forgotten the answer and you think it was hard, go over it. If you remember the answer, there's not as much of a point to it. In terms of, you're talking about the difficulty of the exam given the first and the second ones, it's not always a safe bet because 61A is not curved. And so a lot of people are probably going to take a PMP. I don't think it's safe to bet that the final exam is going to be easier because the class had a harder time on midterm 1 and midterm 2. Like it really is variant. And we're going to try to make it as fair as possible, but the guiding philosophy has always been to make it as similar to past exams as possible so that everyone has a fair chance to study in the same way. So this time it's going to be a little bit more polished than midterm 2 in terms of the test taking environment. So we're hoping that offsets some of the difficulties students were having with technical problems.
Okay.
And doing past exams or past problems you've already done, if you remember the answer, I mean, even if it's not super helpful conceptually, it's still a good confidence boost. So
there's a logistics format question. Yeah, so there's going to, if you want to look at the types of questions, there's a link on the website right now, Ethan. And it's going to be, I expect, yeah, I doubt there'll be like environment diagrams and stuff. Like it should be mostly, it's fill in the blank and multiple choice is the stuff that's supported by our web server. Again, I haven't seen the test, it hasn't been written, but I guess you could have environment diagrams to fill in the blank, but more likely you're going to see more midterm 2 like coding stuff. Don't take my word on that as course staff because I have no inside information as of now. That would just be my like random guess. I think if you do pass exams, that will give you the best regardless.
Yeah.
Hi, question. And do you mean the difficulty will be the same with midterm 1 and midterm 2?
Go for it.
Yeah, so this exam is going to test like some additional concepts to midterm 1 and midterm 2. So really it's going to depend on your own comfort with the newer material as opposed to the material from midterm 1 and midterm 2 scope. And also they're definitely good if you want to use them as practice for questions, but since we've changed the format, like Sean was saying, we're hoping that's going to offset some of the difficulty that people had with midterm 2 in terms of the problems.
There were some problems that were out of scope in terms of difficulty. For example, there's one question, the tree question from midterm 2, we've determined was too difficult. So you shouldn't see anything of that level of difficulty. So because you shouldn't see anything that difficult, but like the other questions are definitely in scope for that level of difficulty.
So should I use midterm 1, midterm 2 as example to do practice, or use the previous exams to?
I'd recommend previous exams, unless you've completely forgotten everything, unless you've completely forgotten all the answers you put for midterm 1. It might be good to review it, but the majority of your time should be spent on new problems, I'd recommend. I don't know. What do you think?
Yeah, no, I'd agree, definitely. They're useful to look over just to see like if you have a pattern of mistakes or concepts that you're having trouble with. But in terms of actual like concrete practice, past exams are the way to go.
How to find the working video for the problems for midterm 1 and midterm 2?
I didn't quite catch that. Can you say that one more time?
And how to find the because usually they will post you will post the video for each problem for midterm 1 and how to find that for midterm 2.
Oh, the assignment, the midterm 2 review videos, are those not up? If they're not up, I think
there's a
they're
link on
making
one
those?
Piazza post.
Yeah, they should be on Piazza, just midterm 2 walkthroughs.
Thank you.
Yeah. Okay. And last question is about practice. And in the lecture, Professor talked about the practice we will post on Friday. And but I'm not sure. You mean the exam, the practice exam we post on Friday and do on Friday, or how long can we work on that?
I think they're planning on everyone taking it at the same time because what they want to do is they want to test the server. So I think if you look at the announcement on the main page, the practice final exam is from 2:10 to 3 p.m. This Friday, so during lecture time.
Oh.
Yeah, so everyone's kind of looking at it at the same time to see if the server can handle so many students using it at once.
Fingers crossed.
Okay. So it's not 9 periods exam. I think I can work on that and have period of time to work on that and then submit that.
It's free bonus points. Yeah.
Okay. Thank you so much.
Yeah, good. Okay.
Yeah, no problem.
Good luck.
Thank you.
Good luck.
Thank you.
I think we can stop the recording there.
Yeah, I'm gonna go ahead and stop it.